Hello, everyone. My name is Andrés Ferragut, and I'm here to present our work on scaling electrical vehicles with uncertain departure times. I'm very glad to be here in performance, albeit virtually. I hope you like the talk. I must say this is a joint work with our student Lucas Narbondo and Professor Fernando Paganini from Universidad of Uruguay. And well, the main idea in this paper is to analyze the charging of electrical vehicles. Why? Because they will become an energy-intensive load to the grid, but users may have some flexibility in their charging times. And flexibility comes in two flavors: flexibility in their deadlines to charge, or in the sojourn time in the system, and also flexibility in the sense that they may depart without a full charge. And in that sense, this sets apart this problem from classical scheduling problems where you have to finish by the deadline. Okay, so the main question here is, how do we schedule these EVs when you have deadlines? And this also begs the question, and this is the main issue in this paper, what happens if we don't know the deadlines exactly? So let's get into it. Our work, the main contribution of our work, is to do a mean field analysis of EV scheduling with uncertain deadlines. And we analyze the behavior of typical policies like earliest deadline first or least laxity first through fluid limits. We also discuss the impact of uncertainty and analyze how to curb some incentives that appear. In the paper, we analyze two policies, EDF and least laxity first. I will focus on this presentation on least laxity first. So let's get into the model. What's our queuing model? Well, you have a large parking lot with individual charging stations. There is an arrival rate of vehicles that have two main characteristics: their sojourn time or deadline, and their service time and nominal power, so how long they will need to charge the vehicle. And you have a maximum capacity C, a maximum number of chargers that you can turn on at the same time. This is due to the electrical grid constraints. Okay, so what's the load of this? This is a many server queue with deadlines. Okay, think of a many server queue with deadlines, and the limitation is electrical power. Okay, so what's the load of the system? Well, it's just lambda times the average service time, as in the Erlang queues. Okay, and we are interested or focused in the overload scenario, when you don't have enough capacity to serve everybody and some reneging will occur. Okay, so what's the least laxity first policy that I mentioned? Well, for every vehicle, you have two main characteristics that are moving in time: the remaining service time and the remaining sojourn time that are being consumed by the system. And the laxity is just the difference between the two. And the intuitive idea is it's the amount of time left to be in service and still meet the deadline. Okay. Of course, if this becomes negative, it means that the system is late in serving you, and the EV will depart with some reneging. Okay, and in fact, upon departure, this reneging will be exactly minus the laxity on departure. So the LLF policy will be just simply to serve the C vehicles with lower laxities at any point in time with preemption. Okay. So how does this behave? Well, we have a previous paper that is in Transaction on Smart Grid in 2019 that describes how least laxity first behaves in the mean field limit. And the idea is the following: when a vehicle arrives into the system, it has some service time, it has some deadline and laxity, which is the difference. And laxity is consumed at the very beginning because the vehicles do not receive service until they are late enough. Okay, so when the laxity becomes negative up to a threshold, they begin service and they depart at time T plus S plus. So what happens here is that the amount of work you receive is just concentrated on this second interval, and you are charged an amount of S, just demand, minus some threshold sigma star 0, which is minus the laxity upon the point. And the system in the mean field limit in overload everybody reneges with some work, sigma star 0 or less. Okay. And what is this sigma star 0, this threshold? Well, it just follows from a capacity condition where the arrival rate times the average work performed on each car should match the capacity. Okay, so this is previous work, and this is how least laxity first works in overload. Okay, so the problem here is that in practice you may know the service time because chargers are smart. You may ask how much battery charge you need, but the sojourn time is based on customer declarations, and therefore they may report them with uncertainty. Okay, so the main question is, how does this scheduler perform when using this uncertain? And so this is the main contribution of the paper. Consider that the system has two deadlines, a real hidden sojourn time that users depart on expiration, but you don't know that. You know some declared sojourn time, or T prime K, which we assume random and possibly correlated with TK, okay? So what the system has at hand to scale the cost is in fact an observed laxity, which is the difference between the remaining service time and the remaining declared sojourn time. So the scaler uses these deadlines to scale precisely and serves them in increasing order of their observed laxity. So what happens here? Well, in fact, you have two laxities, the one that tells you when the vehicle will depart, and the one that tells you when the vehicle will become urgent enough. Okay, so the threshold, the new threshold, L star, which is negative also in overload, or minus sigma star, the amount of work you renege upon departure, will be determined by L prime, but your departure time will be determined by L. Okay, so when you consider all this scenario, in fact, you get that the attained service of a given vehicle is given by S plus the difference between the uncertainty in the laxities minus some first. And the threshold condition is the same as before, lambda times the expected service equal to the capacity. And the remark here is that the threshold only depends on S and the uncertainty, it should say, and the uncertainty down here. Okay, so this enables us to analyze this system. For instance, in some parametric case, in the paper, we analyzed the case of exponential service times and uniform uncertainties. And what we focus on is on individual uncertainties, on individual service. So what's your attained service level on average, given your uncertainty? Okay, and you can compute this. And in fact, we can prove that in overload, this follows this nice expression for exponential service times. And as you can see, it's decreasing in U. So the more over report of your deadline that you do, then the less service you get, okay? In fact, in the paper, we compute the relative gain, which is the difference between the relative difference between what you receive with uncertain deadlines and what you receive in the perfect information case for a given uncertainty level. And this also yields a very nice expression that, as I said before, it's decreasing in U. Okay, so we can compute this model pretty entirely. Okay, and in fact, if you simulate the system, the dots here represent individual vehicles. In the y-axis, you have the difference between received service for a given level of uncertainty and for the perfect information case. And the red line is the conditional expectation estimator from these points, and the green line is the mean field limit. So the mean field limit does a very good job predicting how the system will behave in overload. Okay, so what's the problem here is that, as I said before, if you over-report your deadline, then you get less energy, less service. Okay, so people that under-report the deadlines get priority sooner, and since they are served until departure, this leads to a longer service time. And there is an incentive to under-report your sojourn time. And the question is, how can we handle these misbehaving users? Well, we propose the following modification of the LLF policy, which is to curtail the policy and serve the vehicles as before, but stop service either when the real deadline expires or the declared deadline expires. So if the people say under-report their laxity, they will stop service sooner also, okay? And we can modify our analysis in the same setting. And this is a minor modification of the result I showed you before. The attained service is S minus L prime minus some threshold. But this indicator term guarantees that you don't get more energy if you under-report your deadline. That's the main idea. And this is confirmed by the simulations. This is the same simulation as before with the same vehicles, but using the curtailed version of the policy. And so for negative uncertainty, for under-reporting deadlines, this gain is curved to a constant value. And so you don't get more energy or you don't get any benefit from under-reporting your deadline. Okay. Of course, this is an ideal scenario with Poisson arrivals and homogeneous settings, but we tested this in a real world scenario. I won't go through the details because of time, but thanks to Stephen Lowe, we tested this in a real world scenario that works in overload 73% of the total simulation time, not every time in overload. And the policy with curtailing also does pretty well, also curbs these incentives and works pretty well. So to conclude, we analyzed the behavior of this LLF policy, and the EDF policy is in the paper also. And through a mean fit analysis, we derive explicit expressions for the system performance and provide a suitable policy to curb the incentive to underreport that. So thank you very much, and I'm happy to receive questions.